Today we're going to start talking about the building enclosure. Like we had that graphic in the first class that showed the body, how the human body is similar to a building. We've gone through the foundations, which are the feet. We've gone through the skeleton, which is the structural steel and the supports. We've gone through the materials that encompass, what the flesh and the bones are, and now we're going for the skin. The skin and the hair, the building enclosure, basically what protects you from the environment. So we're going to go through some of the typical methods, typical technologies and materials, and show you how we wrap everything around the structure of this building. All right, so again, basically the elements that we're talking about here is protecting the interior and everything that resides within the interior, the electrical systems, the heating, the plumbing, and the people that are using the building, and protecting them from the outside elements and creating an environment that's usable on the inside. Otherwise, there's no reason to have this building, right? So the things we're trying to protect against are obviously solar rays, lighting, glare, outside air or polluted air infiltration, particularly if you're in the city. Exhaust and stuff tends to carry upwards, and you want the air within your building to be clean so that you're not sitting there inhaling exhaust all day. You're protecting against extreme temperature differentials on the outside. You're trying to maintain a nice 68 degrees or 66 degrees, depending on what's most comfortable for the building setting and most energy efficient. You're protecting the interior and the exterior of your building from the buildup of snow and ice, the damaging effects of rainwater and water. Also, somewhat noise proofing the interior environment, and that goes for any kind of building, from a house to a high-rise building. If you're at home, you don't want your building to be so non-noise resistant that you hear every single honk and horn and car that goes by outside. And yet, we have to find a medium ground that perhaps allows some noise in and doesn't cost an arm and a leg to build that noise-proof building or room. And then, of course, protection against external loads, people, snow, rain, wind, ice, etc. All right, so we've kind of split the topic into two, between roof components and the facades, so basically the sides of your building and the top of your building. So the sides, the skin, and the top, the hair. So there's a number of different components to each one of them. On the roof, obviously, you have the decking, the flashing. There's some insulation up there also, because that's one of the most direct angles of wind and sun, as well as you have to deal with reducing loads on there from wind and rain and snow. You don't want ice buildup, snow buildup to increase the dead load or the weight on your building. All right, and there's a number of ways to do that, and we'll talk about all of that. And then on the facade, there's different kinds of facades that are used in the buildings, and you can see that just walking down a typical avenue somewhere in New York. You'll see brick buildings, you'll see buildings with metal facades or concrete panels. Some of them are built with stone, like we saw some of those great structures when we went through the stone and wood lecture. You could see wood at times when it's family housing. And then, curtain wall construction, which we've been talking about since the first class, basically. And in addition to all those materials, most buildings have windows, so there's going to have to be some kind of glass. There are rare exceptions to that. Some technology buildings that just house data centers and things like that will have an enclosed environment that doesn't require glass. But as we all know, the building industry is tending to go towards more glass and more unique features. And we'll talk about that and how that affects construction cost and your planning for a construction project as well. All right, so on almost any roof, particularly in a high-rise, you'll have a supporting deck. All right, the structure, there'll be a vapor barrier, there'll be insulation, there'll be some kind of roofing membrane, and then possibly even on top of the roof, some form of ballast and flashing. All right, so you see here one of the more built-up roof members where you still have a concrete slab, supporting the roof just like it would be, at the base of your feet on a typical floor in the building. On top of that, there's a vapor barrier because you have to find a way to deal with moisture. And then there'll be some kind of permeable layer on top of that between the insulation and the vapor barrier, which is generally asphalt. Asphalt and gravel, although they form and sometimes tar on the top of a rooftop or tile or shingles, will give you footing, will allow you to walk on the roof and stuff, will give you a soft footing that you're able to move on the roof there without making a lot of noise. And it also gives the roof what we call permeability and the ability to breathe, so that everything above that concrete slab can still be kept dry and free of moisture as the sun warms it up. All right, so a vapor barrier is used where condensation occurs, usually below the roof, in spaces where things like mechanical rooms are, cooking areas. Okay, in a cooking area, there's going to be a lot of steam generated, and that's moisture. Wherever you have a lot of people, heat gets generated. It becomes a little stuffy inside if you've been in a very crowded room, so there's moisture there. In mechanical rooms, obviously, whether you have boilers or water heaters and stuff, anywhere where you're heating a liquid, there could be condensation or some kind of moisture there as well. In the summertime, we've all seen water running down the windows. That water is generated. So you want to reduce moisture and prevent it from getting into the insulation where it could damage the insulation and or grow mold and reduce its effectiveness. And you also want to reduce the vapor pressure on the membrane. So when things get hot and there's more heat and there's more moisture, it tends to expand. And as you know, there's a higher humidity factor and pressure in the air. So you're trying to reduce or just control that so that it's comfortable and that you're not damaging the components of the building. Every material has what we call a thermal resistance, and then that just basically links to your insulation value, so you know how good it is. So that R value gives you an indication as to how good an insulator it really is. Right, and so you see there some of the typical insulators, some of the typical materials, how good they are at insulating and what the thickness would be for some of those insulations, as well as compressive strength, because sometimes it's not only used as an insulation, but it's added as an additional support. So when you're thinking of what material or what method of vapor control and insulation and topping you're intending to use on your roof, you have to think of a couple of things. And number one is making sure that the roof will work in the environment that you're building your building. So a roof, the design of a roof in New York City or Boston is going to be far different from the design of a roof in, say, Florida or New Mexico. Obviously, a lot more moisture, a lot more heat in Florida. You have to deal with more of the cold weather and the changing temperatures in New York or Boston. And then out in the desert, you have a dry, arid climate, with a lot of direct sunlight. You're going to need a different roofing assembly there to deal with it. So not only is it the type of roof that you want, you'll also have to check for the structural requirements of the roof and how you're building it, as well as what kind of load you expect on top of the roof. Many times you'll see roofs that are shaped like triangles, and that's really to facilitate drainage, to prevent buildup on the roof. And then sometimes you'll think it's extremely flat, but when you actually get to the roof, it's sloped so that water and or snow melt will go towards a drain. That's usually concealed and hidden, and then led to the outside of the building and down to the sewer system. So there's a whole different ways, many different designs, many different ways to handle roofing and what you're building. the generals are to make sure that it's strong enough for the location that you're in, that it's built to handle the type of weather that you're in, that if it's a long or wide or very large roof, that you build in expansion joints just like you would on a concrete deck on a floor or on a sidewalk or on a roadway. And that if your roof has equipment on it, as many large buildings do, that you also have to be prepared to handle that load as well as the load of maintenance staff and personnel on top of the roof. So you can't have a flimsy roof even if the even if the equipment is supported internally and the roof is really just the structure around it. But you have to consider that you could be moving new equipment into place one day, that the roof has to be able to handle those kind of loads, plus the people and maintenance staff. All right, so we're going to discuss roof decking a little bit. Again, there's a number of different materials that could be used: wood, concrete, steel, stone, depending on your requirements. And then we have to consider what's going on here. What kind of loads does it have to support? What kind of winds we expect? Is it designed in a manner that'll prevent uplift? Is it sloped for drainage, as we discussed? Will it require expansion joints? And how do we want to finish it? Is it smooth? Do we want a dry-only roof? And is it something that always has to be cleaned or upkept? All right, so there's four major types of roofs that we see generally. A built-up one, where it's insulation on top of a deck, and then something else on top of that insulation, similar to the detail that we showed earlier on with the asphalt and a gravel course and other wearing surfaces on top. Then there are more simple ones that are single ply, that have some kind of material that are laid on and bolted or connected just like you would any other, almost like the siding of a building. There's spray-on and fluid applied, and generally these are waterproofing type elements. They'll look kind of rubbery and be kind of bouncy to the touch when you're walking on it. So you may have a roofing with the spray applied coating there. And generally that coating can be placed on top of the insulation. And then there's also the inverted system, with some kind of membrane placed on the deck and then insulation placed on top of the membrane, which is kind of like opposite of what we do with most of the others, where the insulation's underneath some kind of membrane. All right, so the single ply has a number of advantages, and as we did with basically every option and all our other material lectures, each of those four major types have advantages and disadvantages. And it depends on if it's what you need for your particular use, and it has to be weighed with the cost. So the advantages to single ply, it's this can be not only used as a new roofing material, but you can also use this to repair existing roofs and just put a new single ply over an existing. Generally, they come in rolls or sheets that can be easily placed. It's easy to identify the quantity that you need based on the square foot. It makes it uniform where flashing is based on one material, and generally the warranty. There's a warranty backed by a manufacturer of the material. Typical roofing elements generally get a 20-year warranty, and they're usually pretty thin. All right, so they're kind of thin, strong, flexible, and you don't have too many issues with puncture. You can pretty much drive nails through some of them, and the material itself is good for those kind of applications. But sometimes, sealing joints is a little difficult because they are single ply, so it's not really overlapping. You have one layer, and then if you do have a joint, it's difficult to keep that waterproof and sealed. Single ply again, if it's punctured where it's not supposed to be after installation, there's no backup under it. It's one ply. All right. And generally, these systems require some kind of weight on top of it. As we saw in that earlier detail, there's usually some kind of ballast or asphalt material on top of that to help hold it down and provide some kind of footing. And those materials are, like I said, they're generally permeable, so they don't act as a watertight seal. And if they're mechanically fastened, they're one ply. When you stretch something and it tries to expand in another direction, you may be stressing the material or stretching it, and it may have a shorter lifespan than some other materials. And lastly, if you need heavy ballast to hold in place as a hold-down material, you're adding total weight. You could be adding total weight to your roof, as opposed to some of the other roofing materials, which may be more complex, thicker, more complicated, but actually be lighter. Alright, so here you have a typical example. Again, we have the steel deck. Looks a lot like the steel pans that we use on the floors when we were doing structural steel construction. Right, so the same material basically. So it's like you're building another floor, but you just don't have additional steel on top of it to go to the next level. There could be roofing insulation, that single ply membrane. Those membranes are connected somehow. It could be using a weld, it could be using tar material. A number of ways to make connections, and then on top is the light stone ballast. Right, so here's an example of what it looks like before the ballast is placed. Okay, and you can see how it goes right up the flashing to the edge of the roofs, and you can see the material, how it's connected, and again it has that kind of like rubbery look to it. Right, the built-up roof is the next potential choice. It's a fairly typical roofing design and construction. It's pretty inexpensive, and what it does, it's built up. It has a lot of layers of protection, so you're covering yourself by including many layers. The disadvantages are obviously if you're going with multiple layers, you've got more workmanship, more costs in material most likely. Sometimes quality control is a little bit difficult because you're hiding layers underneath other layers. And with the built-up roof, sometimes it's susceptible to heat and sunlight, where it could impact the material or cause blistering. And then when you get that, you're going to get some deformation in the material, which could lead to water ponding and could further damage the material just by having long-term water. All right, and sometimes this material is not as doesn't have as good a fire retardant rating as other materials and other roof designs. Okay, so mainly because you have all these plies of material and tar or asphalt in between, so you do have poor fire protection ratings with this material. Right, so as you can see, there are numerous layers. Each layer serves a certain purpose, and you can tell it can be pretty labor intensive to have to build up a roof with multiple layers like this. Yeah, and as you can see, that's the byproduct of building the roof. You've got cans of tar and used for asphalt that are shipped up to the roof level and then used and then sent back down for more material. Right. Sometimes the burners and the asphalt heat tanks are left up top so that you have the material right there for where you have to do your work. Right. And then here you see the application of that tack coat for the next layer of material. Just warn you, if you ever have to go to a rooftop or a site where this is being performed on one of your buildings, it's kind of stinky sometimes. Don't wear good shoes. It'll stick to your shoes like crazy. It's just like, building an asphalt roadway. So it gets hot during application. The material stays hot for a long time. And you have to be aware of all those other potential dangers between the heat and the tackiness and the stickiness. All right, just a detail again of what a built-up roofing membrane. This one's a 4-ply one, using the hot asphalt. You can see what the various plies and exposure limits are. Okay. And they put that right directly on top of the sheeting. Again, here's another multi-ply system. You can see this comes up in rolls. Okay, and they're laid and overlapped on top of that tacky surface, okay, to stick it. And again, that's where you have potential issues with ponding and such. If you don't have a good seal between one or two of the layers, water can get entrapped. All right, and again, this guy should not be shirtless. He should be wearing some kind of sleeved shirt and a hard hat and a vest. He has the proper work boots, but not the rest. Okay, and then we go into this version, the spray on or fluid applied, and it's pretty self-explanatory on that. There are different materials that are used, so instead of doing tack coats and layers, you basically have a material that's sprayed on to a certain thickness, and then that hardens or dries and then becomes your roofing protection. They're usually very quick to be applied because, again, they're spray on, just like if you're painting a room in your house and you're using a sprayer versus a hand tool or brush. All right. It can also be applied over another existing roofing system where applicable. These generally provide good insulation, all right, because you're putting a thick layer of material on and building it up, similar to having roofing insulation underneath. They're generally firm up or dry quickly, so they can be applied to roofs that are on angles or triangularly shaped. And it's easy to work this around the penetration. All right, so you have a pipe, you have an exhaust pipe, you have mechanical equipment up on your roof. You just simply spray around it and right up to the edges. All right, so it's not hard to make that waterproof section against any of those openings. Whereas if you're using a firm material, you kind of have to cut. After you cut, you have to do some kind of finishing around it to get it, watertight, and it's much more difficult. And generally, this spray on and fluid applied membrane is very light. Now, the disadvantages are, you kind of have to trust that the mix is correct and try to test it while the materials are going in and sprayed. We do a lot of testing sometimes after it's done, but after it's done, the material's already in place. So if it wasn't mixed correctly and sprayed, it's really, really, really difficult to pull this stuff up and redo it. And that's the same for any application of a spray-on or fluid-applied coating, including waterproofing for roadways, highways, buildings, you name it. So quality control is always the toughest thing to get here. You want to make sure that you have a very experienced crew that knows how to mix this material, and that they don't make any errors in the mix, because the mix is key to production. And again, the same with the experience level. You want it to be an experienced crew putting it on, so you're not overdoing the thickness, overdoing the material, spraying too much consistently in one location where it may be crushing or compacting that material so it doesn't work as well as it should. And then having that good crew will help prevent any other limitations in the application. This is sometimes difficult to slope for proper drainage, although it can be applied to any shape. It's very difficult to get that exact, consistent depth all throughout wherever you're doing it. So you're going to have peaks and valleys, highs and lows, places where things can pond. Okay. And it has to be applied in almost like sections. So that you have time for the material to set and shrink a little bit, most likely, and then you apply your next section, so that it's not one large spray on and then it pulls apart a little bit as the material sets or shrinks a little bit. And then lastly, it's usually a rough surface because you're spraying this on. It's almost like a shotcrete or like the insulation and or concrete that you see sprayed around a steel beam for fire protection. Alright, so I'm going to stop the lecture here and record it, and then we'll pick up right at this slide when we start part 2. Thank you. Alright, let's pick up here in part 2. Again, we're continuing on roofing and the different kinds of roofing, the spray-on and fluid-applied roofing. You can see here a detail with the insulation layer. All right, you can see the roof decking. You can see the roof flashing, all right, which is that section on the left side there. Generally, the roofing membrane will be linked to a higher elevation level on the exterior perimeter of your roof, and that's to give it a place to latch onto and to connect. All right. So you can see how the details are formed there with that foam layer of insulation and then the protective coating on top of it. Okay. And again, here's an example of what some of the spray-on flashing looks like. Okay. You can see that the roof membrane below, and then the spray-on goes all the way up and around the cinder block wall and around to the next wall material over there. All right. So there's an overlay at the flashing. This comes up all the way up the sides. So as you can see, it's kind of easy to spray on. It's you know, but really you're dependent on the skill of the person applying the material and the person mixing the material. So it's kind of hard to quality control this. So it's all in the hands of the applier and trying to make sure that they're using the right materials and mixes. Right, here's an example of where there's a, you saw this listed as one of the R value insulation was the permethane polyurethane foam roof. Right, so this is basically a foam roof that gets applied over everything. So as you can see, just about everything is sealed. All right, all the way up to the connections and up and around it to wherever the openings are, even on those exhaust vents that you see. Basically everything except the actual vent itself is foamed over. So again, the fluid applied roof system can have many, many layers, and they could have other materials in between the fluid applied. Right, so depending on the type of design and what it's being used for. Okay, so here's that inverted deck. Right, you've got the deck, which is the structure. There's the vapor barrier. There's a membrane in between to keep the water out, and then the insulation is placed on top in some kind of material. So it's kind of reverse or inverted from what you would typically expect. And why would you want something like that? Well, again, it depends on where you are. Sometimes that kind of insulation on the top serves better, deals with moisture better than the more typical roof alignment. It in a way could give you a softer walking surface up top where you need it. And again, this could be a material that's placed afterwards where there wasn't insulation before. So you make it so that you can put you know, a water barrier and a membrane and then insulation on top rather than on the interior of your building. Now, one of the more current trends is to use what we call green roofs. And if some of you work on the federal side of building work, you know that all federal buildings are now required to have a LEED rating. And we'll talk a little bit more about LEED itself, which is a from the Green Buildings Council, and it's a way of measuring how earth-friendly or environmentally friendly the construction of your building is. And one of the ways to gain points in that system and some of the other systems that are out there that recognize environmentally friendly buildings is by doing what they call a green roof. And it's by turning your roof into as close as you can to a natural setting. Using plants, greenery, shrubbery, you know, to soak up rainwater, to also provide natural shade and thermal resistance and insulation. So a green roof can also be much more aesthetically pleasing. I think you've seen the picture so far what roofing looks like. It's pretty bland. You know, it could look like that silicone material. It could have gravel. It could, you know, they're not pretty things. Whereas a green roof can actually be used as a sanctuary, as a you know, a place where people go up and eat lunch, bird watch, do that kind of stuff, as well as have a environmentally friendly construction and a natural roof setting. All right, so again, rainwater drainage. You don't have to drain as much of it because it's soaked up by roots and plants naturally, right? And any excess can drain into drainage and then, you know, off into the sewer system. But it's wasted that way, you know. Sometimes green roofs use the captured rainwater to recycle it into other uses. Okay, non-treated water uses like watering the surrounding greenery of the building on the first floor. It could be captured, it could be aligned. So not only is there the water that gets used to feed the plants on the roof, but sometimes green roofs also track this water to other purposes that can be used in the building outside of drinking water, toilet water, wastewater, and again for watering plants instead of using treated water that comes from the water supply system. All right, and the green roof itself is used to heat or cool the interior of the building, reduces the solar load, and actually acts as an insulator. Okay, and you get the added benefits of having trees or plants or grass that can help clean up the air and the environment around you. The disadvantages are obviously you have plants and trees and things that need upkeep on that roof in the future. You need more structural weight to your roof likely because you're holding the weight of the layers of soil plus the materials plus the added drainage. And then it's difficult to identify if you actually have a leak that gets down through the lower levels outside of the exterior. Where is it coming from the outside? Some of them have to be treated or identified from the inside out, which is a much more difficult and costly repair. And then, there is that, like I said, maintaining the green roof itself, making sure it's not getting burnt and then becoming useless, trimming it, keeping it from falling over the sides of the building, etc. So it comes with a little more maintenance. All right, so here is a typical layer of what a green roof will look like, where you have simple vegetation up top, and that vegetation can vary from, grass to flowering plants to even, small trees. And what happens is it naturally gets down into a drainage layer. That drainage layer is sloped somehow to get to drainage, like I said, where that water can be appropriated for other uses sometimes. And then below that, you still need water protection or waterproofing, because just because you want the roof to act like a green roof and be a natural setting, you don't want your roof actually taking on the moisture and things like that. So you still have to put in a waterproofing membrane and a barrier in between there. Okay. What you see there that's kind of unique to the green roofs is the root barrier. It has to be a very strong material that will prevent infiltration from the roots up top, making its way into that layer and then into your roof and possibly causing water damage and or leaks. New York City, if you were to develop with the use of a green roof, you got some tax breaks. All right, and you can see some of the details there pulled from the DOB website. And that was the details of the property tax abatement that they gave back in 2008, 2010. So you can go right onto the DOB website and look for the current reductions and rates if you're interested. Alright, and then lastly we've got the other kind of roof systems, which are basically pitched. We all seen shingles on top of houses like we explained earlier, and those are usually used on those triangular shaped home roofs. Okay, so it's a good insulator, it's a waterproofer, and it allows water to drain down to the drainage system. There's other materials that are used, sometimes metal and industrial, on factories and stuff that don't need to look pretty. Terracotta on houses, and then sometimes even wood as a bare material. But that's not recommended, as wood can be damaged by the elements and is not going to hold up to the water and the rain and the snow and everything for long. Right, that's an example of terracotta. You see those mostly on villa type construction. The typical asphalt shingles, single layer, on top of the wood or plywood roofing. Okay, the metal deck pan roof. Right, this one actually looks pretty good. Some of the negatives to that is it's kind of noisy if rain hits it. Okay. So let's end this section right here and we'll hit roof ballast in the next recording. All right, this is part 3 of this week's lecture, and we're going to continue on with roofing. This is a typical metal roof. As you can see, it looks good to the eye. It's usually a little tougher on the ear, though. Again, if you're in a location that there's hail or heavy rains, usually you'll hear the elements a lot more on a roofing of this type. Steel also heats up. Probably doesn't have the same insulation factor. And you have to probably cool it a little better on the inside. All right, we've mentioned the fact that many of these roofing systems have ballast, and ballast is really just a collection of small stones, similar to what you have, although not as big as the rocks that you see between train tracks. So ballast is used there also to fill in the gaps between ties and rails. But on a roof, it's used to give you a walking surface. It also helps provide some reflection of the solar rays so it's not hitting the roofing material. Ballast can help reduce the spread of fires because it's not a flammable material. Again, it's like rocks, and it reduces, like I said, ultraviolet rays, solar rays. It reduces some of that deterioration of the roofing membrane. But roof ballasts, also do have some negatives to it. All right, it ends up collecting debris and dirt. When there's heavy winds, sometimes the smaller roofing ballast stones can become airborne and then become projectiles off of building tops, which is now a greater concern since Sandy and Irene hit the New York City area, but especially in areas that get frequent heavy wind storms, hurricanes, typhoons, tornadoes, that kind of thing. They're moving away from stone ballast. At times, the ballast gets into your drainage and can clog your drainage. Small pieces like that get into areas where you don't necessarily want them sometimes. And then, after years and wear and tear, you have to often try to redistribute the ballast so that the areas that are walked more frequently aren't exposing your roof or those protective membranes underneath to more of the elements than it should be. Ballast again also becomes hard. Say if you get heavy snow on the roof and you want to reduce some of that snow up there, you can't actually go down to the surface of your roof with a shovel. You have to kind of skim it and try not to lift the ballast up with the snow that you're trying to remove. So again, linking the ballast with the Sandy issues, there were some elements that were identified in building construction through a resiliency task force to kind of make our buildings less susceptible to windstorms. So number one, many with the power supply being located underground and in low-level elevations for the most part in New York City, there was a massive scramble for emergency generators to get buildings up and running again. So you can imagine the size of a generator that's needed to provide power to an entire building. They're not exactly something that are sitting around and waiting for most people to rent in massive quantities. H.O. Penn and other generator manufacturers, Caterpillar will have a couple on standby, but to meet the need that was required after a massive water event, it was very difficult. So emergency generation of power plus an ability to connect or provide a quick hookup to a building with a generator is needed rather than tying into a distribution panel or a switchgear that wasn't meant for a generator. Some ground level improvements that could be made included putting in more sloped sidewalks and tree pits to accommodate the water or overflow of water so that it's not directed towards buildings or the basement of buildings. Again, elevating equipment so that key electrical equipment like generators or even switchgears or power supply or connections are not, and panels are not in the basement of a building and are actually raised above flood height. The implementation of using natural gas generators rather than electrical so that water doesn't affect those as much. And then using manual overrides for things like automatic toilets, which were continually flushing during blackouts or trying to, and using whatever little power there could have been to some of the buildings. There's certain, fail-safes that we didn't think about prior to this kind of an event that we should implement again. And then for rooftop, using pavers rather than the gravel for the walking surface, which are much more difficult to lift up due to their weight. But again, with that added weight, you have to think about what you're going to do with the structure beneath it and how you build your roof if you're going to use a heavier material. Alright, so this is the idea of using a ballast with an overlay, a cover of the walkway over it. So you still get that drainage into a drainage layer, but then you have a more heavy topping and a flat, smooth surface to walk on. One of the improvements that could potentially be made. Right, and that's what those pavers look like. And it's basically like laying thick tile down on the roof. What's the problem with that? Yeah, of course, weight. And then now you have to somehow still provide for roof drainage. And why is roof drainage required? Is basically you don't want the buildup of water or snow up on the roof, adding weight to your roof. If it's cold, it could then freeze and expand and contract and damage the elements of your flashing and your roof and your drainage. So roofs need to have drainage to accommodate this water to prevent cave-ins of roofs. Alright, so there's a number of ways to handle that. Number one is by having some kind of pitch towards a drain on your roof. Right, and that's what they try to do with a lot of those spray-applied roofings. And again, it depends on the skill of the person applying it, that they don't come up with any ponding or low levels and high levels and waviness. Right, the other way is to have scuppers through the parapet walls, right, where the water drains into and out into the drainage system. And or having drains at higher levels on the roof area. Sometimes you'll see what looks like a mushroom-headed steel element with slits all around the circular pattern, so that as water accumulates on the roof, it then goes into a drain, and then that higher elevation head will keep large amounts from water ponding on the roof, and it'll also prevent the gravel and asphalt and other materials from rising up and going into the drain. So that's kind of like the fail-safe. That's kind of like the backup drainage, so that if you do start taking on water and it turns into an enclosed area, that it can only add so much weight, and that you have a secondary drain as a backup on top. So again, drainage is developed through your structural details, how you're doing it. It's also can be based on using tapered layers to provide drainage in between and waterproofing, kind of like channeling or creating canals for that drainage to go, for the water to drain through. And then again, on the spray-on roofing system, there's ways of doing it as well, but you have to basically implement the slope somehow. All right. So here's that tapered system, or a sample of the tapered system. It's called the EPS ballasted system, where you see the details from the deck up. Okay. And all that's leading towards a drain of some kind. All right. Here's a nice detail. I probably should have put this a little bit earlier in the lecture, so you could see what the details are here. That top layer of stonework is called the coping. You have various flashings which you use to layer and overlap on the side of the parapet wall there, which is the extended wall over the roof element. Okay, so you see the concrete roofing there. A parapet is built around your roof. Okay, as you can see the details of how it's in there. All right, so the basically all of that area is waterproof between using the flashings and the cement and concrete material between your bricks, so that any water that hits off of there drains down the side onto the roof. You see that sloped area. It has it could have a triangular wood block behind it that brings the roofing material up, and then the flashing over that ties into the parapet and overlaps that to create that watertight bond. Right, and guides the water down onto the roof. So it's either using a flashing, or you can use an alternate detail with the roulette. All right, So shown below, which basically just ties the roofing directly into an area there that you cement over and make part of your parapet wall. And then once the water gets down to the level of the roof itself, it's angled somehow to get to a drain or a scupper. Alright, so drains are sometimes put in, again, at that low point in a roof as the rest of the roof angles the water towards it. This is an example of that roof drain detail that I told you might be slightly elevated, or as we see on this one, flush to the surface, where it's at a low point. Okay. Again, there will likely be one of these at the low point, or a couple of them, on your roof at the low point. And you see the details there that they use to try to maintain that waterproof seal and tightness around the perimeter of that drain. And again, what I've seen is many times they have a backup drain that if one of these or the whole system gets clogged, there's one at actually a higher elevation that will serve as a backup, maybe an inch or two up, just to prevent extreme weight from being added to the roof should the typical drainage system fail, get clogged, stuffed up, whatever the case may be. Alright, so those flashings, as you saw, as you bring up the waterproofing and the roofing material to the sides of the parapets, are there to avoid water penetrating into the building, okay, along the sides. So say you have a great roof, but if you don't have the right flashing on the side, that water is going to find its way up and around. So you have to make sure that you have a great connection there, that you're building to your details. And there's a number of ways to do it. We saw a couple of the examples before. Okay, here is the flashing that you would use around the pipe penetration. And a pipe penetration could be for a number of things. It could be a water supply, okay, from like a water tank or a water tower. It could be a drain, all right, as we just saw. Or it could be leading down to your mechanical equipment, So it could be, not really only a pipe, but it could be a conduit. Okay, electrical connections to some of the equipment that's on your roof, like say the equipment room of an elevator, ventilation equipment and fans will need some kind of penetration through the roof to get equipment, power and other things up to that, controls. So there's a number of locations on a roof, especially on a large building, that could have systems, and you'll have a lot of openings that you have to find a way to waterproof. Okay. There you see a vent, okay, coming up from a fan, in either a bathroom or a cooking area, and that vent pipe goes up through the roof, and they have to develop a detail to put the roofing membrane and material around there so that it maintains water tightness. Okay, and this is how you put a detail of a roof flashing at a wall. Say you have a structural element where part of it comes up over roof level in the details, or at your connection between two different buildings or two sections of a building, much like a brownstone. Sometimes you have these kind of details on the roof. Okay, so just a sample of what the details will look like. And basically you need to ensure that the material or the roofing system that you use has a warranty that meets your specifications. Okay, each of these kind of roofs have a different length and warranty of time. Like I said, the typical roofing shingle on a house would have something like a 25-year warranty. Other systems have higher length warranties, and sometimes the warranties are dependent on the locations and if they're installed by a certified applier of that material or of that system. Right. So make sure you understand the material and you read all the fine print about what would void that warranty, because believe me, there's a lot of things that would. Right. And then it's not really something that you want to void your warranty on, or not have a warranty on a roofing system, because they're typically expensive. They're time consuming to replace. So if you can afford it, you should maintain that warranty on it. All right, so sometimes there's a prorated way to get some of these systems warranted. Right. And basically it'll over time, because we know that the warranty has a finite limit, and we know eventually the material will corrode and you'll need to replace it. The cost for the warranty could be low at the beginning and go up as time goes on. I've also seen vice versa of that as well, where early on, after your couple of years of warranty, if you want to extend that, it'll cost more as the years go on. All right, but some of the considerations, again, know the fine print. Okay, not only is there a length of time, but sometimes these systems require maintenance, proof of maintenance as well. So you may have to have the manufacturer come in and do an inspection or witness the maintenance as it takes place. You'd have to probably have a maintenance plan and other things showing how you will perform the maintenance on those roofs. Warranties sometimes only replace the material, doesn't cover the labor. That's another thing you have to look for. Just like any other warranty, if the damage was caused from the interior, not the exterior where the roofing was meant to protect you from, probably not included. There's a number of exclusions depending on what you might have in the vicinity of your roof, what kind of equipment. All right, and acts of nature, acts of God kind of things are usually not covered also under a warranty. So typical with almost any other construction warranty or equipment. All right, so we're going to pick up here. We'll leave off at warranty and we'll pick up on roof inspection in our next segment. Okay, so we left off on roof warranties, and again, we know there's certain restrictions on how much you can actually warranty a roof. We know eventually whatever roofing system that you use, will give way and have to be replaced at some point. Typical, 20, 30, 40-year warranties are fairly typical. And just make sure that you understand what the limitations are to those warranties and what's covered, and what you have to do as an owner or an operator to maintain the right to that warranty. Okay, so typically, for a building, an owner, operator, maintainer, you're going to have to continually do roof inspections. Good inspection plans pretty much with the change of seasons will go up and do a thorough inspection of the roof. Easy signs to know something's not exactly perfect with the roof is that there is no ponding, or that there is ponding. That means you're not properly sloped to all your drainage, and now that you have an area that's going to retain water and possibly could fail first. But again, depending on the roofing type, some are more applicable or more able to withstand things like ponding. It could just mean that it was like a poor application, and that water will go away when it gets hot and the sun hits the roof, and won't be a problem. But if you have severe ponding, there's an issue. That can also add weight in a localized area, and then that could be the first area of structural failure if you have an extensive amount of ponding. So you likely don't have the proper slope if you have ponding somewhere. You want to make sure that you have flashing at all the key elements to protect leakage behind that flashing, or in between, seep through those tiny openings. You want to make sure that all the penetrations are properly sealed. Alright, we saw how that can be done on one of the slides before. A number of layers of material leading up to the mouth of where the penetration is, and just making sure that those are nice and sealed. If you've got a non-green roof that starts growing vegetation, have an issue. There could be roots that start going through various layers of your roofing, and it's not designed to do that unless it's a green roof. Alligating means basically it's starting to wrinkle up and get like alligator skin. That would mean the heat's having an effect on the material, that it's shrinking towards one area and stretching towards another. Again, could lead to weaknesses in certain locations. Fish mouthing, almost the same ideal. One area is getting thinner, the other area is getting wider, possibly due to temperature effects or the loading on the roof. If your insulation ever seems wet through inspection, there's a problem there and it's supposed to dry off or not get wet at all. And then again, keep a good eye on areas that are most heavily traveled on the roof, near equipment, near things that you get to and from often, because not only are those the most heavily loaded areas, it's also getting the most traffic of people on the roof going to and from to check on it, work on it, whatever the case might be. Alright, so, obviously the most indicative factor of a failed roof is from the inside you're getting water. But that's not the only way that a roof is damaged. There could definitely be damage to a roof before it gets to that, and you'd like to identify it through these steps before you have water infiltration. There's a couple of ways to test a roof. As I said, depending on the way it's designed, there are different methods of trying to test depending on what the installation type is. There is an ASTM standard for roofing testing, and this really should only be done when they're certifying a roof in a factory and showing that their product is applicable and that it can meet the limits that they state in their manufacturer's literature. But you can't actually take this testing. It's like a live load test of the roof by flooding the roof, making sure that there are no leaks. That's a great test, but it's also, what happens if you do weaken your structure by doing this and it just doesn't fail, you're that much closer to eventually failing. So, it should be used sporadically only where necessary as required by a spec maybe, but it's probably a little further than you should go in terms of testing a roof installation. We like to say use the first rainy day or first heavy storm to really test out your roof. And, that test, what it does is make sure all the drainage works properly where it's supposed to, that the areas that have flashing get sprayed with water, and make sure that there's no seepage behind it, and all the joints are sealed so you don't get water infiltration coming down through there. Alright, so there are other standards, and these are some of the other standards typical in the industry. The FM standards, Factory Mutual Insurance Company. It's a criteria for roof hold down during wind conditions. And then you'll see an FM and an I 60, 90, 120 basically referring to whatever the wind speeds are that it's supposed to hold up to. And then even though design criteria is stated somewhat differently, the testing for the insurance company goes in wind speeds. And 60 is a fairly weak wind speed. Every year, past 10 years have probably broken days with 60 mile per hour winds. So, 120 is more typical. That's hurricane rated, and that's usually what you'd want for the minimum. And again, the design of your roof and the roofing material have to be considered together. Right, the higher your building is, obviously you want you want to live up to the higher standard because you're exposed to higher wind speeds up there. The height of the parapet walls are important because those serve as a barrier to wind. Okay, so if you have a higher parapet wall and you have almost an enclosed 7-8 foot high roof deck, a lot of your equipment and your roofing material would be very protected from that wind, and that's ideal. And again, just putting up parapet walls is extra expense on the building, extra materials, but it could actually be beneficial for the life of the roof. ASCE-7 is the wind criteria that has to be included and reviewed as part of the design. Now, other ways to test a roof if you know you have some issues and you're only getting the localized leakage, but when there's one leak, there's probably others on their way, so you might want to do some kind of testing. Infrared is a way to do that testing, and what it does is detects moisture in the roofing. So what happens is, a roof during the day, it's taking in sunlight, it's taking in heat, taking in energy, and heats up the roof. At night, when the ambient air or outside air is cooler and the roof is warm, you're going to see that heat radiate back out. And obviously the wet insulation is going to hold in more heat because you have water in there that's warming up with it, and then as it gets cool at night, it's going to come out at a higher rate as well. And so what that does is it shows up on these infrared graphics, and it shows you exactly where you're having issues with your roof. So you see the infrared graphic to the right, and you see on the left the areas marked out of what needs to be fixed. So really quickly, take a minute to look at this. What would you say the issue is with this roofing design or installation? Okay, and so from what we know, your issue is where the flashing is. Now typically you want flashing to either come up and over the parapet wall, but in this case you have a high parapet wall, so what you would like to have is that angled entry. As we saw earlier in class, down in that right angle where the roofing membrane curves up into the flashing, generally you'd have a triangular block underneath there, forcing that up on an angle, and then the flashing entering the parapet wall at some point and then sealed. This kind of flashing to parapet wall connection will end up eroding up by that connection, and then once you get any kind of erosion there or shifting of the flashing or the parapet wall, you're going to end up getting water infiltrating behind it, coming down underneath the roof membrane, between your roof deck, insulation, and then eating away at the parapet wall as well. So this is a poor looking design or construction. Alright, so we've completed the section on roofing. We're going to move into exterior walls. Obviously the exterior walls are very important to the building in that they're the primary defenses of the environment on the exterior, all four sides of your building or whatever the perimeter of your building is. They obviously have to be designed for wind loads. They have to be able to hold all the live loads of the building and the live load of the exterior wall that's above them. So depending on the connections to your structure, some of the exterior walls actually have to be what we call weight-bearing walls. The structure itself must be capable of holding the dead load of the material and the live load. Okay, same as any other structure. But with the exterior walls, what we're looking at is that we're adding weight, all right, and depending on the connections and how those walls are supported, your structure has to be designed to take that as well as part of the dead load. Again, just like with the roofing material, anywhere you have a joint or a break or a change in materials from wood to brick, or brick to the windows, or whatever the difference is, wherever you have those joints, those are the most critical areas to keep sealed. Because generally the first areas where you have water or wind intrusion. And again, as part of the design, any anchorages, connections, things like that, however you're fastening this material to your building or to the other portions of the wall, those have to be designed to support all the weights, both live loads and dead loads. Right, so curtain wall construction, which is pretty common in New York City, as we saw in the first class, curtain wall construction has been pretty common since the 50s and 60s in New York City. Brick has been around far longer than that. One of the first major exterior wall materials. Stone, same. Metal can be used as an exterior wall on prefabricated buildings, hangars, at airports, facilities, used for construction or fabrication shops. Those could be metal type buildings, and then concrete panels as well on some of the larger buildings. So when you're using those exterior walls, the ways that you connect them, the curtain walls will have glass and mullions, and we'll show you what a mullion is in a minute. Brick, they have lintels and angles to help connect them to your structures. Stone, again, stone angles and clips if you're doing some kind of fancy stone design. Metal uses panels and clips as well, and concrete panels use panels and clips. Alright, so if you're using precast concrete, you will probably design or fabricate the lifting lugs into the sections so that when the panel is built at the factory, they can be lifted using these lugs or connections, picked by the crane, put on the flatbed, sent to the site, and then using the same lifting lugs placed in their location on the building. So as you see, panel width 8 foot, and that's really just so it can accommodate the typical width of a tractor trailer flatbed, so it could safely fit on that and be transported. Okay, here's a couple examples of brick exterior walls. Two buildings side by side, built at different times, right up to their lot edge lines up against each other. You can see the different type of pattern, different type of brick, and different color. So each of them probably link back to a particular time to show when it was constructed. Alright, so facades are very important, especially in a big city. If they start to deteriorate, they can become very, very dangerous. As we're walking down the sidewalk. Any building that has a weak facade could have issues. So there is a very robust facade inspection safety program in New York City. Here are some of the requirements. All right, so take a look. Put this up there for a couple minutes so you can just read through it. Obviously, anytime you're identified as having an unsafe facade, the public has to be protected. If the building is still in use, basically what you have to do is erect a sidewalk bridge or sidewalk shed so that folks can travel underneath that on the sidewalk in safety. So if any kind of piece of the building starts falling out, smaller pieces, they'll be protected by basically a steel bridge above their heads. And you have to have that in place until there's an inspection and proof that the violation or the safety issue has been rectified, and then you can take down that bridge. Right, so metal panels, very typical construction. You see this a lot in office buildings, airports. All right, it's usually a very quick construction because again, the metal panels fasten directly to the structure. They're fairly light, can be easily lifted and cherry-picked into place by smaller cranes. And then the more difficult and the more common for skyscraper-type construction is the curtain wall construction. All right, so every part of the curtain wall will include the mullions, which is how they fasten, how the frame of the curtain wall fastens to the structure, as well as provides a similar connection to your glass and windows. Okay, there's various ways of installing the glass and types of glass that will go into a curtain wall system. And then there's different ways to try to seal out the elements during your installation, including caulking, prefabricated and installed gaskets on each section of the curtain wall, and taping. So those are the typical elements. Okay, so here you see a cross-section of what a typical ceiling of a curtain wall looks like. this is kind of blown up pretty big. It's about a 4-inch section where the two sections of the ceiling, the curtain wall, come in. Alright, so the glass frames into the mullion, alright, which is that central piece, onto a setting block. There's a gasket in there that provides the seal between the glass framing and the mullion. Right, so it gives you that the seal of both water and wind. Right, so that fits snugly into there. And then the bottom of the mullion rests on the curtain wall section below it, which has a very similar detail. And basically you build up using the same connection type piece. Just another version of the same kind of detail. You can see it can get pretty intricate. And this is fairly common. Okay. And as you can see, it also has the same kind of gasket type system to make it a snug fit. Right? So it's compressed against the window. And what this one has, it has actually small holes in the framing below it. So if water does get through, it weeps or drains into the lower section and then out. So just another typical cross section. Again, caulking was a common method of sealing between panels. Right, so obviously, just like you're caulking around the home, around the bathtub, around the section, making sure that the surface is properly prepped, cleaned, and dry is critical. Making sure that the caulking material that you use will tack to whatever you're putting it on. Right, so you have to make sure certain caulks are stick better to certain materials than others. So you need to make sure you have the right material on hand, and that it's also rated for, the same thing that the windows or the mullions or whatever your caulking is rated for. Because obviously, if it's not, then the caulking automatically, even with good application, becomes your weak point. Okay. So very often, when you see something like a caulking or a compound seal made, what you'll see is the use of what they call backer rods, and that's basically a foam 1-inch, 2-inch round foam rod, similar to maybe like a pool noodle, that gets stuffed into the opening, and then on the front of that end you start your caulking. And what that really does is, number one, it gives you something to caulk against to form a seal, and it also reduces the amount of caulking you need to use to make your seal. Okay, so that's a typical detail in construction now, is the use of backer rod. Alright, so again, here's a kind of the front view of glass sitting in a mullion frame. Okay, the glass gets set on blocks. Within the mullion, what you would see if it wasn't cut away here is that the mullion actually extends up over the glass, but the setting blocks are there. It prevents the glass from actually touching the metal, and then it forms a section for drainage and weeps. All right. And then if you're using the windows up and through, there's a difference between the panels that you're using as actual windows, and then the similar looking panels that are in areas that there's no view between floors, that hide the the structure of the building, that hide the all the areas where all the mechanical and lighting and electrical equipment is, until you get to the next floor where you'll have again a vision type panel where you need to see out. Right, so it's a different makeup, different material. Right. So here you can see there's the vision glass, then the spandrel glass, vision glass, spandrel glass, and it goes up in that pattern as you go up. Right, so it's almost the same color. Try to get it to match as good as you can, unless you're, intentionally trying to make definition between floors of your building. All right, and again, glazing is a very important part of this whole process, how to get it up and in. Right. Critical on a glazing system is obviously, again, designed to support the weight, wind pressure, all the forces that are against it, possible deflection, bending forces, the fact that all the materials in the system have to expand and contract and be accounted for either through expansion joints or having similar materials so that they all expand and contract at the same or similar rates. And again, you're trying to avoid metal contacting glass, not only for that drainage and support, but also the fact you don't want, in the metal movements of the building, whether it's swaying, whether it's bending, whether it's expanding with heat or cold, or contracting with cold, you don't want that glass and metal to contact, as it could damage the glass. Glass comes in many different types of fabrications: tempered, laminated, tinted, like the window panels that you just saw on the slide before, insulated glass like we kind of have in our homes and in just about every building. They could be double layer, triple layer. They could have gas between layers of glass to help their R ratings, and then anneal glass. Okay, and they all have various strengths. Tempered is one of the strongest glasses used. Okay. Laminated, which is exactly like it sounds. If you have a laminated ID card, there's like a thin polyvinyl sheet over it, and what that does, it's a safety glass. So if somehow the glass is broken, the lamination kind of keeps the little piece of the glass together so that it doesn't fall out and break into pieces. Right. Tinted and reflected, obviously you're using those to reduce glare, right. Possibly keep a room cooler. Right. Insulated, as I noted earlier, it could be double, triple space glass with either air on the inside or a gas that actually heats up hotter to create better insulation. And what basically that does is there's air or a gas trapped between two panes or panels of glass in a window, and as sunlight hits it, basically that material within the window heats up. Okay. And even when the sun goes down, it remains somewhat hot and gives you better insulation. Alright, so this is kind of what it looks like when tempered glass breaks into granules, so you might want to have tempered glass that's laminated. Okay. So as you see here, the lamination is actually on the interior between two sheets of glass. So whichever side breaks or heats or somehow, it basically both stuck to that singular layer. Tinted reflects a lot of the sunlight so that you don't take as much heat inside. Right, just like your sunglasses or tinted windows on your car. heat from the inside gets bounced back towards the inside, and heat from the outside gets redirected and bounced back outside. So it's good at holding in, and it's good at preventing heat. Alright, so here's the detail of insulating glass. Right, so you have your two panes of glass, and inside there's a sealant and a spacer. The spacer is what basically makes that gap between the two. It's a hard material. You sandwich that with the two panes of glass, put a sealant in there to maintain the air tightness, and then whatever you want to put in that airspace, you put in the airspace. So it could be, like I said, just typical air, or another kind of gas like argon, which has better capabilities of heating up and insulating. Okay. So here's just another corner cutout detail. See the two panes of glass with the spacer. Shows you where they put the identification of the window. Right, so basically, if you go into any window, or most modern windows, you should be able to identify who the manufacturer is, and there'll be some identification marks on the inside to indicate what kind of glass it is. Right, so this is the stick system of erecting glass. And you can see you have both horizontal and vertical mullions. So you're basically building this like a checker pattern. Right? Fitting each panel at a time. Moving your way over, sliding it down, and then capping it with the top mullion. Using that top mullion, the other side of it is the base for the next layer of glass. Sliding it between two verticals and then putting another horizontal. And what you see there is the hopping between the vision panel and the non-vision panel going on up. Now the panelized system basically come in sections, and you kind of like hang them on anchors. So they already have their seals and spans in place, and they'll have a connection to the anchor on the inside face, and the anchor will be tied directly into the building structure. So again, same way, they're building a piece at a time, but they're kind of they have their sections already done. They slide right in and then connect to the building structure. All right, so this is a real example of that panelized type thing. What you see there are the hoist systems that feed your building. Okay, and you can see there's like a doorway at every floor of the building. So as they're building, they're going on up. And remember what we said the negative was for the hoist system is that you have to go back at the end, take down the hoist, and then fill in whatever exterior detail you're using, whether it's bricks, concrete, curtain wall, glass. And you may have already had those crews in and out, and they have to come back and just basically do the detailing for this section where you had the hoists in place to service your construction needs. So again, that's why you don't want to have overkill in the number of hoists that you put in your building, that you have to use a realistic amount that can not only serve your building but also not take away a lot of the workspace. Alright, so you see some of the safety within, even though mullions are in place in many of the panels. You can see there's still a couple panels that need to be placed. So what do? We have to put in some kind of fall protection or netting in those vacated areas and maintain that until we have the structure sealed. So here you go. You see the framing and the mullion details, right? And then sliding the panel down through it, and then clipping it to the structure. Which is probably what the guys on the, as you can see up there by the connection to the crane, right. And see, you can see here some of that exterior detailing. That's how that those clips and connections are installed within your building. Right there, you see it kind of exposed and opened up. Okay. This is looking out, all right, from the floor, out through the window. Okay, in the center, coming down black, is the mullion. You have your curtain wall clips. They get fastened onto the anchor, and the anchor is tied directly into the structure. And all that gets hidden behind the interior walling, so you never see it. Again, a similar type detail with some finishing and insulation in a non-vision panel. And what we'll do is we'll stop right here and allow this to record. Alright, and let's finish up with the final section of lecture number 6 on exteriors and walls. Okay, so what you have here is the curtain wall detail, and this is a section through the floor, so I wanted to walk you through this and so you can see what you've got. And just to give you the perspective, if you look to the right, the finish line of the ceiling is that central line on the right side. So this connection and this mullion between the two, the spandrel glass and the vision glass, that connection takes place right at about the ceiling level, ceiling up to the floor structure, okay, of the next floor. Right, so basically what you see on the lower section is the vision glass, right? So you just have the glass panel, and the glass panel gets inserted up into that mullion. It has a little bit of silicone sealing behind it, again trying to make that snug fit. Right? And this particular detail and you can follow the weep path up through the mullion to the spandrel glass, so you can see where, if there is infiltration, how that comes right back out. It doesn't make it to the interior. You can see physical separation, as you can see, centered in the support of the mullion between the two glass panels. Right? So that is always kept to the exterior of the building. And then when you get up to the spandrel glass, you can see that right behind that they're going to install insulation. You saw the back side of that in the previous slide. Okay. And then again, behind all that, you have that flooring. I'm going to flip back up a couple slides here just so you can see. Okay, so right behind, you see how there's a gap there between when you make the connection and down at the edge of the floor, the poured floor for the concrete. We're going to talk about that in a little bit. Again here, you put in that couple inches of insulation in between, and you can still see there is a gap, right, between where the structure of the core concrete structure of the floor ends, and then that insulation, which is basically the end of your exterior. Alright, so mullions, again, they're also part of the exterior structure. We look at them as kind of like connections and supports and stuff, but they really are a structural element as well, and they have to be protected. So there's strength considerations, and then you have to have some kind of coating on them to ensure they can also hold up to the weather, the same weather that the glass panes have to reflect. Okay. Okay, and then the fact that when you see the detail, okay, there's air gaps in between. Right, you see where that aluminum cover is that goes on the outside or the exterior, and then there are air gaps in between. Okay, and what that does is it reduces the exterior heat or cold from transmitting from outside the mullion through the inside section. So it's almost like an insulating layer, similar to like a double glass pane with the air in between. So again, here's another section, another typical design. The gaskets, the different pockets. Okay. So as you can see, they're very intricate pieces that have to be fabricated, and they have to meet very strict fabrication tolerances to be able to work with the panes. So basically those sections and mullions are created using a process called extrusion, right, where the material is pushed through a die. To break this down to the kiddie level, it's almost like the Play-Doh. You know how it comes with all those extruders and piston forces that aluminum, the heated aluminum, through a die, and it comes out in the extruded shape. Okay. Cooled. Okay. Just a shot of some of the construction during One World Trade. And you can see the pane system there. Okay. Now the glass is being erected. And again, anytime you have an atypical shape, it becomes a very difficult construction. You can see how it's angled and it's triangular in certain sections. It's sloped inwards. Now you have glass panels that are of different sizes and shapes, mullions with different angles, interior detailed sections and clip angles that are going to be different for a lot of those sections of glass, so it makes construction a little bit more difficult. And as you can see, they started the typical curtain wall panel up about 10 stories higher than the surface entrances. Okay. And you can see some of the details of the structural steel exterior and protection there, concrete walls, etc. All part of, basically security measures that were taken in the construction and the final design of the building. So curtain walls obviously have to be tested as well. And number one, for an exterior wall on a large or tall building, wind loads are very critical. And the way you test it is usually you do a mock-up of some type, test it in a wind tunnel, and then you perform a couple of other tests, a combination of factory and common sense type tests, air and water infiltration, the expansion and contraction of the materials as a composite, with the two, with a couple of stories worth of panels and connections. See if there's any deflection, failures of the material. While doing this mock-up, you actually find out how constructible it is. So you can see how difficult it is to erect in a factory versus how it will be in the field. Right? Always easier in the factory. Okay. And then obviously wind pressure, just like you would in a wind tunnel if you don't do the wind tunnel test. Okay. So as we all know, as the higher up you go in the building, you're going to have higher wind pressures, just more exposure to wind, less wind breaks, buildings around you and things around you to slow the wind down. But the reaction you want on the other side is a distributed reaction, um, where you're not taking extra load. It's acting as a composite unit, right? And you don't want, just because you're taking more load or more pressure at the top, you don't want the building bending or having to bend and react more at the top too. So a good rigid design with a little bit of leeway will give you an equivalent to a distributed pressure reaction on the other side. So wind speeds and directions that you have to deal with are important to consider. There's pretty much known data everywhere that you're going to construct from weather reports and such, so you have an idea. Of course, there's always those outliers like the hurricanes or tornadoes or storms that could hit, but you have all that data historically as well, so you can try to design to that or more. The geometry of the building is very important when it comes to analyzing the wind loads. Right? It's a whole study of aerodynamics, the science of aerodynamics, and how wind reacts around certain patterns and shapes. Again, proximity of the buildings have an impact in terms of they're kind of like wind breaks, or they could turn into wind tunnels. Okay, have you walked down a Manhattan street and felt like you were going to be blown over, but then you go walk down an avenue, you make a right or a left and end up on the avenue, and you feel like there's no wind at all. All right, because basically the streets are open from end to end, from river to river. Prevailing winds usually go west to east. So if the wind is coming right through that way, it could be really windy, but then you're walking down an avenue between two 60-story buildings, you hardly feel anything, right? Because the wind is coming down the streets, and then the buildings act as buffers. The same thing happens to other buildings. Okay, if you're building in an area that's surrounded by other buildings, you'll probably have less wind loads. You could have shear loads on those areas, like on the streets. Okay, but direct hits from wind, you're more likely to have those on buildings that are at the exterior of the island, 1st Avenue, 11th Avenue, wherever you might be. And the height of the building. Of course, the higher up, you're exposed to higher winds. The higher up, you also have less buildings around you to help deflect the wind or serve as windbreaks around you. Okay, so wind zones in the United States. Basically, the way it reacts, again, prevailing winds usually come from west to east. Higher winds also start from the north towards the south and kind of dip down into the Central Plains states. And what happens is you have the wind makes it through, the Rockies and mountains, and then hits an area where there's relatively flat land and nothing to break the wind, and that's why you have such a high wind zone in the central states there. Okay, basically they're flat, and then they hit another mountain range, the Appalachians and others, as you get towards the east, which kind of breaks the wind and deflects it a little bit, to the point where the further you go east from that wind zone, it starts slowing down again. So, as you can see in New York, it's fairly low wind zone compared to the rest of the country. And what we do scientifically to study things, and it's not just airplanes or space shuttles and things like that, but you can also do wind tunnel tests on architectural mock-ups of buildings. And what you see here is a building that's being built in the city. They basically did a whole to-scale model of the city to be able to see what the effects of the surrounding are on the new building construction. Okay, and what you'll get is a report, something like this, that comes back that will show you where you take the most wind load. And obviously you might have to build a more robust section or reinforcement in that section. And then you also use these results to factor back into your design and figure out what you need to do to accommodate this. Will you need something to rebalance the building? Will you have that shock absorber type system somewhere on the top floor? Or can you build without that and just rely on the structure itself? Right, so here's basically a mock-up of, this one's an aircraft engine, but same idea. You build it to scale just like you would normally construct it. based on your design. And then not only do you have wind in there, you have water, you have other elements in there that you can use to test it. So what's being tested by all this wind and water and stuff? You're testing for air infiltration in areas that you don't want air. Will water get into places where you don't want it? Does the glass hold up to the pressures and the winds applied? Do the design drainage or failure protection design elements work, like weep holes? So if water does get in, does it go out the right way? Does it travel through the right way, or does it get to somewhere where it shouldn't? Expansion and contraction of materials are important. Okay, you use that in mock-ups. So what we saw for that gap between the wall and the concrete floor, this is something that's probably been tested, right? Based on the expansion and contraction of the structural steel and concrete. You know you have to have some kind of gap between there and your outside panels so that the floor is not forcing the panels out and trying to pop them out into the street. Okay, you're also looking for other elements of your design in terms of lateral movement, structural integrity, impact, constructability. So again, when you're installing a curtain wall, some of the things we want to do, okay, what kind of factors are we looking for? We just talked about a couple of them in the wind factory testing. Okay. Give yourself a minute, try to jot down a couple of things. All right, what are we testing for and why? All right. So when you're building that or designing for that curtain wall, you're always looking for deflections, right? To make sure that your design is not going to create a tension zone there at the edge where you're connecting to the curtain wall. Right? You want to make sure that those connections are fairly rigid at the exteriors, so that there's not a lot of bend over there, right? Things that could loosen up, extra pressures, extra tension, things you don't want in a connection with an exterior portion. Concrete creep. Okay, again, you don't want you need to know all of the details of what you're building. There could be expansion and contraction. Right, so that's why you have that kind of gap between the sections there, as well as total movement of the structure. You want to know how much is going to move from wind, seismically. Designed for the max, so that even if you get that maximum movement, okay, your connections and spacings are right, so that your exterior isn't falling off. And then lastly, locations. Typical stuff for construction is just measurements, locations, elevations of anchors, placements, making sure you have the right types so that they can mate properly and fit up correctly. Right? This is just a typical Primavera schedule of where these anchors are going to be placed. Okay, and again, everything works together. All right, those anchors are placed when you're doing the concrete flooring in the structure. So you have to have your anchors linked into your structural steel, and then when the concrete gets poured, it gets poured right around it. Right, so you can have that. The anchor goes right through the concrete floor, tied into the steel, so it's sturdy and it can't move. Right. So I've seen times where those anchors hadn't been placed when they should have been, or one out of the two anchors were placed in certain locations. And to correct that is very difficult. You basically have to drill through something you've already built and make a connection. Usually using some kind of epoxy now, because you can't go right down into the steel because you don't have a bottom nut to it. Or you could go up from the bottom and the top and do it, but that's even further. So you use some kind of epoxy joint with an expansion anchor. Not perfect, but it's a way to solve a problem if you have it. Right, so all of these have to be considered. So when you're in construction, Just because the steel's up and everything's in place doesn't mean you're ready for the next step. Okay. So before you pour that concrete for your floors, you gotta make sure that every detail in regard to what's going into that floor is there. Sometimes it's not just reinforcement. Some floors have conduit embedded into it, piping embedded into it. Obviously, these anchors for the exterior walls embedded to it. Right? So make sure that all your drawings match up, that you have a working drawing that calls out all the elements. Okay? That it's not just the framing of the concrete or the rebar, that you actually have everything in place. And it's very important to have coordinated drawings. So those working drawings are just as important as the contract plans or shop drawings. And it's usually on the onus of the contractor to develop those working drawings, because they're usually a combination of a lot of trades or a lot of elements. Right? So your steel fabricator is not going to do it for you. The concrete firm that you hired to do all your concrete work is not going to do it for you. But you as the general contractor, if you are the general contractor or owner, will have to have proper working drawings. Alright, so the homework for this week, based on the lectures and the readings, I'd like you to just explain what each of these roofing systems are. Give me a description of what it is, what materials are used. It doesn't have to be anything too lengthy, a quarter page, half page on each, and just describe it, right, so that I know that you've understood each of the four major roofing systems. Okay, and that's it for this week. So as usual, that homework's due in a week before the next class. Okay, anytime before, just email it to me, and you'll get credit for it. And thank you very much for listening to this